Asoodeh. He's a faculty at McMaster University in Canada, and he'll talk about contraction of Markov kernels and differential privacy. In this late afternoon sessions, you're going to see a lot of names that Ilya listed in the end of his talk, Daniel, Sabrushin, and so on, appearing. So it's going to be exciting. Go ahead, Shahab.
Okay, great. Thank you so much, Flavio. And thank you for being here. And a big thank you for the organizer, for Lalita, Flavio, and Oliver for putting together this kind of timely and great workshop. Okay, so I want to talk about contraction of Markov kernels and applications to differential privacy. So the talk is the talk is based on my collaboration with Flavio and Mario, and I have to say that this is going to be a two-part talk. The first part will be given by Mario right after this talk. Okay, so let's just talk about the outline. So at the beginning, I would talk about very briefly talk about the definition of differential privacy. I think after Ilya's keynote, I don't have to spend time on the definition. But after a very quick definition of differential privacy, we will define hockey-stick divergence, which is a certain instance of F divergence, and then after that, I would talk about the contraction coefficient of Markov kernels, and then we will see, what's the connection with the DP. After that, as an application of this kind of contraction coefficient in DP, I will talk about privacy guarantee of hidden state projected noisy SGD. First, I will discuss the previous work, the state-of-the-art results, which basically assumes that loss functions are convex and smooth. And then after that, we will talk about the more general case, our result. Just to give you a very quick preview of the result, we will show that the privacy guarantee of hidden state projected noisy SGD converges as the number of iterations goes to infinity. So we can run hidden state projected noisy SGD as long as we want with a non-trivial privacy guarantee. And then the last part, we will talk about kind of the same setting, but without projection. So we are going to talk about the hidden state projection-free noisy SGD, and Mario will talk about this in more details. Okay, so let's dive in. So suppose we have a data set X containing information of a bunch of individuals. We compute some function on this data set, but because of the privacy issues, we cannot really just release that function X publicly. What we can do, we can just pass it through some privacy preserving mechanism K, and what this mechanism does is basically just generate a distribution. Okay, so the output is K of X, which is a distribution. Okay, so now we can look at a neighboring data set X prime. So basically X prime and X differ in only one entry. So the last entry here, we compute the same function on this data set, but it's going to be different because of the data sets are different. So let's call it X prime. And then again, we pass it through the same privacy preserving mechanism, and the output will be another distribution K of X prime. So this is a variant of Ilya's picture in his slides. So again, as he mentioned, differential privacy kind of dictates some sort of distance between these two distributions for any neighboring data set X and X prime. But what is the measure of distance here? So the original definition of epsilon delta dp was based on hockey-stick divergence. We say that this mechanism is epsilon delta dp if the hockey-stick divergence between K of X and K of X prime is smaller than delta for any pair of neighboring data set X and X prime. And what is the hockey-stick divergence? For any pair of probability measures mu and num on some space W, the hockey-stick divergence between mu and nu is basically just for any measurable set, you look at this subtraction, so mu of A minus e to the epsilon nu of A, and then you maximize it over all measurable set A. So this is the definition of the hockey-stick divergence. So it's exactly the same definition as Ilya's, but here I'm just using hockey-stick divergence in the definition of the epsilon delta dp. Again, as Ilya mentioned, we can define hockey-stick divergence in terms of the Renyi divergence. Okay, we can say that K is alpha epsilon RBP or Renyi differentially private if the Renyi divergence between K of X and K of X prime is smaller than epsilon, again for any pair of neighboring data set X and X prime. Okay, so again, as Ilya mentioned, a very important property of epsilon delta differential privacy, and also the Venn differential privacy, is the post-processing property. And post-processing actually says that by post-processing the output of a mechanism, we are not going to lose any privacy. And more precisely, if I have a Markov kernel psi, then the composition of K and psi will always improve the privacy guarantee. Okay, so more mathematically, I can say that if I look at the composition of K and psi, then the composed mechanism will be epsilon delta prime dp for some delta prime, which is strictly smaller than delta. Okay, and now the question is, how can we quantify this privacy amplification? Okay, so the question is, what is the smallest delta prime such that the composition is epsilon delta prime dp? Okay, so if I can quantify this delta prime, then basically I can quantify the privacy amplification. So again, mathematically, I can formulate this problem as follows. Okay, so I'm looking at this Markov kernel psi, then I consider this two input distribution mu and nu. Okay, so mu and nu are the output distribution of my mechanism corresponding to neighboring data set X and X prime. So mu and nu are very close to each other according to the heuristic divergence. Okay, so now I have these two input distribution for my Markov kernel psi, and this input distribution induce output distribution on this kernel. Okay, so for mu, the output distribution will be psi mu, and for nu, the output distribution will be psi nu. Okay, so think of this as the output distribution of my channel psi. Okay, so now the question is, what is the largest output heuristic divergence among all mu and nu, such that the heuristic divergence between mu and nu are smaller than delta? Okay, so again, mu and nu are the output of an epsilon delta dp, so we should have this two constraint on the on mu and nu. Okay, so now the question is, how can we compute this this maximization subject to this constraint on the input distributions? So one way to answer this question is by introducing contraction coefficient. Okay, so we are looking at this channel, this Markov kernel, two input distribution and two output distribution, and contraction coefficient is basically just look at the ratio of the output heuristic divergence over the input heuristic divergence, and then we maximize it over all choice of input distribution mu and nu. Okay, so we all know this in information theory, because of data processing inequality, for example, we know that this is always smaller than or equal to 1. If there exists some Markov kernel for which the contraction coefficient is strongly smaller than 1, then we have non-trivial contraction coefficient. Okay, so this definition immediately gives us this type of inequality. Okay, so the output heuristic divergence is smaller than the input heuristic divergence times the contraction coefficient. And this is what information theorists call strong data processing inequality, or SDPI. Okay, so strong because if I didn't have this contraction coefficient, this is exactly DPI, but now I'm just putting something here which is potentially strictly smaller than 1, so I'm just kind of improving my DPI. So now, if I know that the heuristic divergence between mu and nu is smaller than delta, then I can get this kind of simple upper bound for the output heuristic divergence, and hence I can quantify the privacy amplification by post-processing. Okay, so the composition of K and psi is epsilon delta prime dp, where now delta prime is just delta times the contraction coefficient. Okay, so this is just a very simple application of the contraction coefficient to quantify privacy amplification by post-processing. But now the question is, can we actually compute the contraction coefficient for general Markov kernel psi? Okay, but before I talk about the computation of contraction coefficient, let me just talk a little bit of history. So this quantity in a contraction coefficient, we can define it for all general F divergences. Okay, so we have the ratio of the output F divergence over the input F divergence. And people in information theory has been working on this, has been thinking about this for almost half a century, well, more than half a century. It goes back to Differential, where basically he looked at the contraction coefficient on the total variation distance, and he proved a very, very simple characterization for the contraction coefficient. So his result is actually very, very important. It has many applications in statistical physics, dynamical system, of course, information theory, Markov chains. It has many, many applications. Wittenhausen actually look at the same kind of definition, contraction coefficient on the chi-square divergence, and then show that there is a nice connection with the Renyi maximal correlation. And then Allschmidt and Gatch, they look at the contraction coefficient on the KL divergence, and then they show some very nice connection with the decay of mutual information on the Markov chain. And then after that, there are so many works on kind of different properties of contraction coefficient for general F divergences. But none of this work is actually about the hockeyistic divergence, not surprisingly, because hockeyistic divergence is relatively young in information theory community. In 2020, in a collaboration with Mario and Flavio, we kind of proved a nice characterization for the contraction coefficient under hockeyistic divergence, and this is what it looks like. So for any Markov kernel psi, the contraction coefficient under hockeyistic divergence is basically it can be computed by this maximization. So we look at just 2 points in the input. So we look at the hockeyistic divergence between psi of y and psi of y prime, and then we maximize it over all choice of y and y prime. Okay, so, and remarkably, this is very, very similar to the 2-point characterization of Dubrushans in 1956. Okay, so let's just have an example. So let's just look at the Gaussian kernel. So what Gaussian kernel does is, so we denote it by chi sigma g, G for Gaussian. So what this Gaussian kernel does, it basically just add noise with variance sigma square to the input. Okay, so so the input will be just Gaussian with mean y and variance sigma square. So we can think of this as a Gaussian channel, and we know that in information theory, every time that we talk about Gaussian channel, we always put some constraint on the input. Okay, so the constraint might be peak power constraint or average power constraint. So using this theorem, we show that if the Gaussian kernel has peak power constraint, meaning if the input is always bounded, then the contraction coefficient of Gaussian kernel is actually given by this function theta epsilon evaluated at R over sigma, where now this function theta epsilon is just depends on this Q function. So it has a very, very simple form. Okay, but if R is infinity, meaning we don't have any peak power constraint, then we can show that theta epsilon actually goes to 1. It kind of increases to 1, meaning there is no so contraction coefficient is actually trivial. Or again, if you have average power constraint instead of peak power constraint, again, we are not going to have any non-trivial contraction coefficient. Again, it's going to be equal to 1. Okay, so there are several works on the connection between contraction coefficient and differential privacy. There are these 4 papers. They look at this sort of contraction coefficient for central differential privacy, the setting that we talked about at the beginning of the talk, and also for the local differential privacy. There are several works on contraction coefficient depending on for different kind of F divergences, and they prove some cool result in local differential privacy. So in the remaining of my talk, I want to focus on this on this work. And we want to talk about the privacy guarantee of noisy SGD. And we post this paper just a few days ago to archive. Okay, so let's just talk about privacy guarantee of hidden state projected noisy SGD. I will talk at the beginning, I will talk about the state of the art result, and then we will talk about that result. Okay, so so one of the most basic algorithm for differentially private machine learning is noisy SGD. So this is exactly a classical SGD, but we just add Gaussian noise. Okay, so in the first iteration, we just pick some random point from some distribution mu on the parameter space. So this W is the parameter space. And then in the first iteration, we just take the mini batch and then we use it, for the gradient descent. Okay, so we take the average of the gradient of the loss, we multiply by eta, and then we subtract it from the previous model parameter. Okay, and then we add noise. We add IID Gaussian noise with variance sigma square, and then at the end, we just take the projection onto the parameter space. Okay, so let me write this algorithm in a more compact way. So here, instead of that gradient descent, I just use this function psi. So this psi function, for any batch of size b, this is actually my update function. Okay, so and after t iteration, I stop and then I output all the model parameters, all the intermediate steps. I just publicly release them. Okay, so the output is W1, W2, all the way to WT. There are so many works on privacy analysis of this algorithm, and all of them are based on some version of composition results. Okay, so we compute the privacy guarantee of one iteration, and then we apply some composition to say something about the privacy of the overall algorithm after t number of iterations. The best DP result gives us epsilon that scales as root t, and the best RDP result gives us epsilon that scales as linear in the number of iterations. So both of these results are vacuous when the number of iterations is very, very large. Okay, so epsilon increases, actually goes to infinity if t goes to infinity. And again, so epsilon here for RDP goes even faster when the number of iterations goes to infinity. So what these two results implies is that if I want to have a given level of privacy on my SGD, then I have to find some upper bound for the number of iterations. And that means the accuracy of the model training is going to be suboptimal. Okay. So after this work, after all this noisy SGD, there was a very interesting work by Feldman et al. In 2018. They proposed actually a hidden state noisy SGD. Okay, so what they proposed was that maybe we don't really have to release all the model parameters. I can just train my machine learning model and only release the last iterate. Okay, so all the model parameters will be hidden, and I only release the last iterate. So WT is the only output of this algorithm. It's the intuition behind this model is that, okay, so by hiding all the intermediate iterate, probably I'm going to improve the privacy of the overall algorithm, and hopefully, the privacy does not go to infinity if the number of iterations goes to infinity. But unfortunately, this their proof technique is still vacuous when the number of iterations goes to infinity. Okay, so 2 years or 3 years after their work, this kind of breakthrough came along. So Chaurasia, Yi, and Shukri in this paper, they proved that under some assumption, the privacy guarantee actually kind of converges. Okay, so they look at noisy SGD with these three assumptions. Okay, so at the mini batch size is equal to n. So basically, the mini batch is just full batch. The loss function is strongly convex and it is smooth. Okay, so then under these assumptions, they prove that Renyi differential privacy parameter of noisy GD, the gradient descent, converges as t goes to infinity. This is an incredible result, a very, very powerful result. They prove is great. Basically, what they showed was that instead of having some sort of linear dependence on the number of iterations, so look at all these dashed lines, for the hidden state GD, the privacy guarantee actually converges. So I can run GD as long as I want without having kind of non-trivial privacy guarantee. Okay, so here the plots are given in terms of different order of Renyi divergence and different levels of strong convexity. Again, this is an incredible result, but those assumptions, the full batch, strong convexity and smoothness are not very practical. Okay, so they do not actually tell us anything about the practical private training. So 1 year after these two papers came along, by Ye and Shukri and Altshuler and Talbot, they basically relaxed, various assumptions of the previous work. Okay, so in the first paper, they kind of relaxed the full batch assumption. So again, the loss function should be a strongly convex and a smooth. In the second paper, they relaxed the full batch assumption and also the strong convexity. Okay, so the loss needs to be only convex and a smooth. Okay, and then under these two assumptions, they proved that Renyi differential privacy parameter of noisy SGD converges as T goes to infinity. Again, very, very interesting result, very counterintuitive results, but the assumptions are a little bit restrictive because nothing in deep learning is strongly convex, not even convex, and definitely not as smooth. So both of these two papers actually pose open question as to kind of relax this convexity assumption. The first paper says it remains an important open problem to further relax the convexity and the smoothness condition for proving converging Renyi DP bound. And the second paper says convexity is too restrictive when training deep networks, and it is an interesting open question if the assumption of convexity can be relaxed. And they went on to say that this appears to require significant new machinery as our techniques break down in the non-convex setting. What we are going to do, we want to come up with some convergent upper bound for differential privacy parameter, not RDP, but differential privacy parameter for arbitrary loss function, convex or non-convex, smooth or non-smooth, but for a variant of noisy SGD. And what is the variant? The variant is what is now known as DPSGD. Okay, so DPSGD is the same as noisy SGD. The only difference is that at each iteration we have to clip the gradient. Okay, and what this clipping does, the clipping just gets some clipping constant C, and it kind of clip the gradient if the norm is going to be smaller than C. Okay, so what it does is, so if this is my gradient, if the norm of the gradient is smaller than constant C, then I just grab the direction of the gradient and I break the norm exactly at C. Okay, so this is DPSGD was proposed in this paper, Abadi et al. In 2016, and I believe it's one of the most popular algorithms for training private deep models. Okay, so this is our result. So the informal version of our result. So we showed that DPSGD is epsilon delta DP for any epsilon, and delta is upper bounded by this ratio. Okay, so here P is B over N. So think of P as the subsampling rate, and this constant theta is a constant between 0 and 1 that depends on a privacy parameter epsilon, learning rate eta, clipping constant C, noise variance sigma square, and the diameter of the parameter space. Okay, so what is important here is that this upper bound actually increases as a function of T, but then at some point, this constant, if T is sufficiently large, this term here just disappears, and what we end up with is just P times theta divided by this guy, which is way smaller than 1. Okay, and then this actually gives us that convergent upper bound that we wanted. Again, so we can run DPSGD as large as we want, as long as we want, and then still we have some sort of non-trivial privacy guarantee. Okay, now let me just make it a little bit more formal. So here the theta constant is actually this theta epsilon. So remember, theta epsilon was the contraction coefficient of Gaussian kernel. But here we evaluate theta function as on this constant. So the diameter of a parameter space plus 2 times eta times C divided by the variance. So hopefully that makes it clear that there is a strong connection between a privacy analysis of DPSGD and contraction coefficient of Markov kernels. Okay, so let's just see what this bound looks like. So here I just pick this set of parameters. Epsilon is equal to 3, and then for a given value of epsilon, the upper bound is actually something like this. So again, after almost 10 number of iterations, delta converges to something like 0.002. Okay, so we converge pretty quick. Okay, so this is So here I'm fixing epsilon and I'm showing the convergent behavior of delta. We can just turn it around. We can fix delta. Delta is now 10 to minus 3. And then we can see that, epsilon converges to something like 3.2, again, after something like, 10 number of iterations. Okay, so again, we can run DPSGD for practically infinitely many number of iterations, and still the privacy guarantee is not going to be worse than 3.2, for example. So again, very counterintuitive result. Okay, so I'm not going to talk about the proof. I want to just go over some technical ingredients in the proof. Mario will take over and talk about the details of the proof. There are 3 technical ingredients in the proof. The first one is we are going to just express DPSGD as a composition of T Markov kernel. This is not an entirely new representation of DPSGD. Feldman et al. They kind of implicitly did that as well. So in the second part, we are going to kind of present a new privacy analysis of DPSGD if each of these T kernels satisfy what we call coupled nonlinear DPI, coupled nonlinear data processing inequality. If each Markov kernel satisfies this condition, then we can have a very, very simple privacy analysis for DPSGD. And then in the last part, we prove that each kernel in DPSGD with gradient clipping satisfy this condition, satisfy coupled nonlinear DPI. And then the proof here is based on the contraction coefficient of Gaussian Markov kernel. Okay, so let me just talk about the first ingredient. So here, suppose we have this data set of size n. So in the first iteration of Markov kernel, in the first iteration of DPSGD, I just take the mini batch B1, and then I use it in the update function psi, and then I add Gaussian noise, and then at the end I do the projection. Okay, so then composition of these 3 functions constitute the first Markov kernel. Okay, so this is K1. Okay. So the second iteration is exactly the same. So I take the second mini batch B2, I use it in the update function, add Gaussian noise, and then do the projection. Again, this is going to be the second Markov kernel, and so on. Okay, so we have T Markov kernel, each of which will have 3 parts. The kind of the subsampling given by this mini batch, a Gaussian additive, and then projection. Okay, so again, if I have another enabling data set X prime, so suppose that X prime has so it differs from my original data set X only in the first entry, then we are going to have exactly the same Markov kernel. So the first iteration will have the same kind of 3 components: the update function psi prime, adding Gaussian noise, and then the projection. The only difference between K prime 1 and K1 is basically this update function psi prime. Okay, so if this differing point happens to be in my first mini batch, then psi prime and psi will be different. Okay, so we can precisely find the probability that psi and psi prime will be different. Okay, and that probability is just B over n. Okay, so if 1 is not in my first mini batch, then psi prime and psi will be the same. So that means K1, this Markov kernel and this Markov kernel will be the same for these 2 neighboring data sets. Okay, so we have the same. So the same, the next iteration will also be represented by this Markov kernel K prime 2, and again we have this set of Markov kernels for this data set X prime. If I initiate my DPSGD with this input distribution mu, then in this case, the output will be, the output of my algorithm after T iteration will be this distribution. And then for the other data set, the output distribution will be this. And what I have to do, what I have to prove in order to compute the privacy guarantee of this algorithm, I have to look at the hockey-stick divergence between the output distribution, meaning this distribution and this distribution, and then show that this hockey-stick divergence is smaller than some delta. And then I will be done. Okay. And then in order to do that, we prove a small lemma. So we showed that if for each of these Markov kernel KT and K prime T, if each of them satisfy a coupled nonlinear data processing inequality, meaning if there exists some constant between 0 and 1, alpha T and beta T between 0 and 1, such that the stochastic divergence between KT nu and K prime T nu for two arbitrary distributions mu and nu is smaller than alpha T times the stochastic divergence between mu and nu plus BT, plus beta T. If we have this condition that we call it coupled nonlinear data processing inequality, then we can very easily compute the stochastic divergence between the output distribution. Okay, so the stochastic divergence between the output distribution will be upper bounded by this term. Okay, so now all I have to do is to prove that for DPSGD with gradient clipping, there exists such constant alpha T and beta T. And then I just plug it into this formula, and then I can just be done with the proof. So how to do this? Stay tuned. Mario will talk about this the third ingredient. So as the last slide, I want to just talk about the takeaway message. Here we show that for hidden state noisy SGD with gradient clipping, no private data leaks after a small burn-in period. So it's something like after 10, 20 number of iteration, the privacy guarantee actually converges as T goes to infinity. So again, we can run DPSGD as long as we want without having kind of trivial privacy guarantee. And the proof was based on two very information-theoretic concepts. The first one was this kind of coupled nonlinear DPI condition. And the second one was the contraction coefficient of Gaussian kernel. So, so information theory is actually very, very essential. It's actually crucial for proving such counterintuitive results. So we have an open problem. So the open problem here is that, do we need projection for this result? Can we kind of get rid of projection and still have the same result? So hopefully Mario will also talk about some sort of evidence for this open problem. I think I will stop here and take the question.
We have time for a couple of questions while Mario sets up. So.
This is Ilya. So I think the result is wonderful because it captures our intuition that the longer we run DPSGD, the more private, or at least we don't lose privacy as it goes along. Mm-hmm. My question is whether you believe that the delta that you have, it's catastrophic, like there's it hides some dragons, or it's an artifact of the proof technique?
Okay, so delta hides some dragon. What do you mean by that?
Well, with probability delta, all bets are off. The privacy gets violated.
I think so. Yes. So yeah. So this is approximate DP. So we have that nuclear option, that nuclear event that you mentioned. We have it there, absolutely. But
artifact of the proof technique, or it's actually captures some underlying phenomenon.
I think this is, I would say this is a very underlying phenomenon. And because, all this previous work, this three work that I mentioned, they keep working on the Renyi differential privacy. Okay. And then there is no that nuclear option, for the Renyi differential privacy. But as far as I know, there is no way that we can prove the same result for Renyi differential privacy if there is no convexity. So I think this kind of nuclear catastrophic, privacy violation is kind of the underlying phenomenon for DPSGD. We cannot prove it for RDP.
Interesting. Thank you.
maybe we can take the other questions offline, or maybe you can ask it to Mario at the end of his talk. So our next speaker is Mario Diaz from UNAM, and he'll be continuing talking about contraction of Markov kernel